After getting somewhat familiar with microchips, electronics and the I2C communication protocol, I decided to build my own device. I call it the output controller, and it's basically an AVR chip in slave mode that controls a bunch of shift registers. By stacking multiple registers on top of each other, or next to each other really, I should be able to drive an arbitrary number of outputs with the help of a custom-made I2C instruction set. However, this video has nothing to do with any of that. The shift registers that I got are of type SN74HC595N, 8-bit wide, and they're serial to parallel. That means that data is shifted in sequentially and outputted in parallel. What's special about this chip though is that they are latched internally. In other words, there are two registers, one for shifting and one for outputting. Naturally, there's two distinct clock lines, so both registers can be controlled individually. One clock is used to load data into the input register, the other clock transfers all data at once from the input to the output register. This is an important feature because otherwise the bit shifting would immediately show on the output side. Now, because I don't have any patience and also I want to make sure that they work properly, I wanted to give it a try in a simple setup on the breadboard. As you can see, we've got the chip here, 8 LEDs connected to the parallel output using 330 ohm resistors and 2 jumper wires, one for the input and the other for both clocks connected together. Now watch me shift in some data by plugging the jumper wire from 5 volt to ground back and forth. In theory, every time the clock input detects a rising edge, it should do something. Instead, as you can see, it's messing up completely. There is a couple of reasons for that. First, once I unplug the wire, the clock pin is left floating, so the input is undefined and who knows if the chip has internal resistors. Secondly, the input pins are really sensitive, so when I plug the wire in, it doesn't produce a single clean edge, but a massive amount of noise as the pin grinds into the hole. In conclusion, I guess it's safe to say this is just a shit setup. So what we need is a device that produces a nice clean clock signal, and this is where the 555 timer comes in. The 555 timer is a multi-purpose chip that allows a bunch of different configurations depending on the way you connect external stuff to it. There is a million tutorials on how to do that in detail, so I'm not going there. The mode of operation that I'm interested in is the so-called astable mode. You can find the schematics on page 10 in the datasheet. Astable means that the output signal on pin 3 alternates between high and low periodically, which is exactly what I want for a clock. I modified the schematics slightly using an online prototyping tool. If you ignore the different layouts, you'll realize it's almost identical. Resistor A is R1, capacitor C is C2, and this 0.01 microfarad capacitor connected to pin 5 is C1. The only difference is that resistor B is divided into R2 and a 100K potentiometer. That means that my resistor B can be anything between 1K and 101K, which will affect the frequency. If you go to the next page, it gives you a bunch of formulas how to calculate the frequency. I copied them into a spreadsheet so I could play around with them, and here's what I came up with. The values for RA and C are 1K and 10 microfarads. The value for B changes, like I said, between 1K and 101K. According to math, that should give me a frequency range between 0.7 and 48 Hz, which is perfect. Having a stable clock is certainly a useful thing, but sometimes you might want to stop the clock and advance manually. Luckily, the 555 timer offers a solution for that as well. It's called monostable operation and is described on page 9. Again, there is a trillion tutorials on that, so if you're interested in the details, go check them out. Basically what's going on here is the output pin stays low until the trigger voltage is pulled below 1/3 of the supply voltage. When that happens, the output goes high for a moment until the capacitor has charged up to 2/3 of the supply voltage. Then everything goes back to the original state. This makes sure that whatever is connected to the output receives exactly one clean rising edge. Once again, I have copied the schematics to easy EDA, with a few minor modifications. In particular, the trigger on pin 2 is implemented using a pull-up resistor and a button to ground. For this setup I'm using a 1 mega ohm potentiometer and a 1 microfarad capacitor. That should give me a delay of up to half a second depending on the fine-tuning of the potentiometer. The timers would look something like this on a PCB. The other PCB is used for switching between the two modes, driving several LEDs, combining the timer signals into one final output, etc. I wouldn't pay too much attention to it because it's missing a few things that I forgot and had to add later. Now let's move on to the box. It's quite a fancy box, I gotta say, and at first I thought it might be a little too fancy for this trivial circuit that I'm making, but it turns out they're really fucking cheap on eBay, and if I were to make one myself from scratch it would be 20 times as expensive, so I decided to just go with it. The front panel got some holes for the switch, the clock potentiometer, and the trigger button, and a bunch of LEDs indicating which mode is currently active, and the state of the outputs of the two timers. The back panel is going to get the DC input, the clock output, and an extra ground wire for convenience. Now you might have noticed that I've got two clock wires hanging out here, so I should probably explain why that is. If we go back to the shift registers situation, you might remember that I mentioned two clocks, one for the shifting and one for the output. In order to achieve deterministic results, it's clever to have both clock signals shifted by half a period, or in other words, inverted. And this is exactly what the second clock output does. When this one is high, the other one is low, and vice versa. Also, these wires are thicker than the ones I normally use on a breadboard because I don't want them to get damaged. Before I put everything together, let me just go over the second PCB real quick. The first 4 pins connect to the other PCB. We've got 5 volts ground, the clock signal, and the button signal. The first 4 transistors are used to drive the LEDs, and they're all part of the same configuration. It starts at 5 volts, goes through a 330 ohm resistor, through an external LED, back into the circuit, into the collector, out of the emitter, and into ground. The base is always connected over a 4.7K resistor to some control signal. The first 2 transistors are triggered by the 2 timer signals. The second 2 are triggered by the state of the switch that controls which timer should be outputted. On the other side of the board I've got 2 logic chips, the 74HC08 AND gate and the 74HC32 OR gate, which combine the timer signals and the switch state into a single output. The last transistor at the bottom is used to create the inverted clock signal. The 2 resistors next to the switch connector are pull-down resistors for the gate inputs. And that should be it, I think. And this is what the assembled product looks like. I've got 5 volt DC plugged in and the clock wires screwed into this terminal. From there, the clock and inverted clock wires are connected to the shift register on the breadboard. I don't need ground here because it's the same ground that's already on the breadboard. As you can see, both the clock output as well as the buttons are working in the background, while the switch control switch signal is forwarded to the output wires. In case you're wondering where the input is coming from, I've got the last bit of the register connected to the input, so it's just looping through whatever is currently stored in the register, but most importantly, it's not messing up anymore. Okay, that's it for now. See ya.